Hello everyone, this is Pratibha. Today I'm going to discuss about how to convert NFA with epsilon to DFA without epsilon. And this subject is Automata Theory and Compiler Design. And the subject code is 21CS51. First, we know about the steps for converting epsilon NFA to DFA. In this method, we try to remove all the epsilon transition from the given non-deterministic finite automata. The methods is mentioned below. The step 1 is find out all the epsilon transition from each state from Q that will be called as epsilon closure. Step 2, then transition can be obtained the transitions means in the epsilon closure on transition moves. Step 2 is repeated for each input symbol and for each state of given NFA. The last step is by using the resultant status the transition table for equivalent NFA without epsilon can be built. Next, we move on to the example of convert the given NFA with epsilon moves to DFA without epsilon moves. Here the NFA with epsilon is given. Solution. We will first obtain the epsilon closure of each state, that is, we will find epsilon reachable states from the current state. Hence, epsilon closure Q equals QRS, epsilon closure R equals to RS, epsilon closure S equal to S. Epsilon closure Q means with null input or no input symbol we can reach QRS. In a similar manner for R and S, epsilon closure are obtained. Now we will obtain del of transition for each state and each input symbol as shown as below. First we need to find out Q of A equal to the epsilon closure del of epsilon closure Q comma A. Q is a epsilon transition moves and A is a input symbol. Epsilon closure del of Q comma A is a Q, union del of R comma A is a null, union del of S comma A is a null. Epsilon closure Q, Q is a epsilon transition modes equal to the QRS. Next, del of Q comma B equal to epsilon closure del of epsilon closure Q comma B, epsilon closure del of Q comma R comma S and input symbol is B, epsilon closure del of Q comma B union del of R comma B union del of S comma B. Epsilon closure del of Q comma B is a null, del of R comma B is a R, del of S comma B is a null. Epsilon closure R means transition moves of epsilon is R comma S. Del of Q comma C equal to the epsilon closure R epsilon closure Q comma C. Epsilon closure del of Q comma R comma S is input symbol C. Epsilon closure del of Q comma C union del of R comma C union del of S comma C. Epsilon closure Q comma C is a null and del of R comma C is also union and S comma C is yes, epsilon closure yes, epsilon transition moves of S is a yes. Next, del of R comma A equal to epsilon closure del of R comma S and our input symbol is A. Epsilon closure del of R comma A union del of S comma A. Epsilon closure del of R comma A is null and S to A is also null. That means del of R comma A equals to null. Del of R comma B equals to epsilon closure del of R comma S and input symbol is B. Epsilon closure del of R comma B union del of S comma B. R to B is R and S to B is null. Epsilon closure R, epsilon transitions moves from the R is R comma S. That means del of R comma B equals to R comma S. Del of R comma C equals to epsilon closure del of R comma S and input symbol is C. Epsilon closure del of R comma C union del of S comma C. Epsilon closure R to C is null and S to C is yes. Del of R comma C equals to S. Del of S comma A equals to epsilon closure del of S and input symbol is A. Epsilon closure del of S to A is null. That means del of S comma A equals to null. Del of S comma B equals to epsilon closure del of S and input symbol is B. Epsilon closure S to B is null. Del of S comma B is also null. Del of S comma C equals to epsilon closure del of S and the input symbol is C. Epsilon closure del and S to C is yes. Del of S comma C is yes. Next, we move on to the DFA without epsilon transition table and diagram. These are all new states, and ABC is a input symbols. For diagram, we can refer this table. These three states are final states because of NFA with epsilon diagram. S is a final state. From QRS state, A goes to QRS and B goes to RS and C goes to S. From RS state, A goes to no transition, B goes to RS and C goes to S. From S state, A goes to no transition, B also no transition, C goes to S. Here some advantages of this method. Deterministic nature. DFA are deterministic, meaning that for any given state under input symbol, there is exactly one transition. This determination simplifies the understanding of the automation's behavior and makes it easier to analyze. Efficient implementation. DFA are generally more straightforward to implement in practice. They can be efficiently simulated using a simple table or switch case statement, making them suitable for hardware and software implementations. Predictable behavior. The absence of epsilon transitions eliminates the non-determinations and makes the behavior of the automation more predictable. In an NFA with epsilon transitions, multiple paths may lead to the same state for the same input, introducing ambiguity. Performance improvement. In some cases, converting an NFA with epsilon transitions to DFA without epsilon transitions can lead to a more efficient automation with faster recognition times for input strings. Easier formal analysis. DFA are often more enable formal analysis, simplifying tasks such as proving the equivalence of two DFAs or demonstrating the properties of the language accepted by the automation. Simplification of the transition table. The transition table of a DFA typically more compact than that of an NFA with epsilon transitions. This can lead to the reduction in memory requirements and more efficient representation of the automation.